Excuse me, sir, but you are on mute, sir. We can't hear you.
Okay, okay, okay. Fine, fine, fine. Did I unmute myself?
Yes, sir.
Okay, great. Okay, wait. Let me see if the okay the board is visible. I guess is it
Yes, sir.
fine? Okay, I'm still combining the files. I think it has been some. It's still showing me some 4 minutes left. I hope that in a few minutes it will be able to combine it into a PDF. They are actually all JPG images. So in a few minutes I will share it. Okay. I'm left with some questions and some topics before I move on to some other unit operation. Like I guess I will start with drawing. Okay, but before drawing, I have to complete some topics because these kind of tidbit questions are being asked. Okay, okay. First, I'll just quickly memorize you people. What was 4 years law? Let's start. Uh, if you remember what was 4 years law, Q is equal to anybody who can tell me heat transfer through a body, conduction heat transfer
Minus K into A into dt by dx.
minus Ka by dx. Great, fine. Now we will further, and this was formula number one. Okay. Now we will further add few formulas. Okay. Sometimes if it is just given the conduction you have to find for a few bodies, then you will use this formula. Okay. But if sometimes it will be asked to you, this is conduction, conduction heat transfer. Okay, for anybody, fine. But if it is a case of composite wall, okay, we have some walls. Okay, I'll just one thing. Now this was the case of conduction heat transfer. This is general formula. Now what if there is a conduction heat transfer for a composite wall? This will be our second. Okay. Suppose there are two or three walls. Suppose one, two, three, or four. Okay, or three walls. Suppose there are three walls. Okay. Now we are applying heat. Fine. This is T1. This will be here T4. Fine. Okay. It will be T1. This will be T2. This will be T3. Suppose there are two walls. How do you find the heat transfer for a composite wall? Okay, there are discrete walls. There are two discrete walls, and we have to find out the heat transfer through each of them. How do you find it? So we have formula for it. Just remember this formula. T1 minus T4. This will be divided by T1. This will be T2. This will be T3. This will be T4. Okay. 1, this will be 2, this will be 3. This will be divided by, it will have resistance, this will have resistance, this will have resistance, R1, R2, R3. So remember for a composite wall, we have a formula, okay, our file has been downloaded, R1 plus R2 plus R3. Okay, just remember conduction heat transfer for it may be asked as a multiple choice question. What is the formula for a conduction heat transfer through a composite wall? Just simply write Q is equal to T1 initial temperature minus final temperature divided by the resistances that are occurring between them, that are present between them. Okay, this is simple formula. There is no big science in this. Simply remember conduction heat transfer for a composite wall will be T1 minus T4 divided by R1 plus R2 plus R3. Simple. There is no, I think there is no big science behind it. Okay, fine. First, I shall transfer you the files. Just wait for a second. This is our lecture 5 or lecture 6?
5.
5. Great. Downloads, and then we will call it as lecture 5. Where is it, lecture 5? Okay, since I'm using phone right now, it is aligned properly. Somebody give me your mail ID who will upload it to the group. Somebody share your mail ID who has high speed internet. Then later, in a few minutes, you can simultaneously upload it on the group. Or I shall do it myself. This is done. Let me first share it then. We'll do one thing. I'll go to send and then I'll share it. This is food engineering class. Okay, great. Great. Okay, fine. Then we have the third formula. Okay, third heat transfer. Why I haven't got this? Okay. This is asked more frequently. This is our third, conduction through a hollow cylinder. Fine. When this is I think this is more frequently asked. Sometimes they will just ask you the formula. Okay. Sometimes they will only ask you about the formula, but sometimes they may ask you about sometimes they may ask you about a numerical, a small numerical, just formula based. They will give you all the datas. Like, okay, first I shall write the formula. Okay. Remember, for a hollow cylinder, the formula will be 2 pi Lk T1 minus T2 whole divided by ln of R2 by R1. Okay. Suppose we have a cylinder. Fine. This is a hollow cylinder. Understanding me? It will have two radius. Because the thickness, there will be some thickness now on the outer wall. So I will assume that we all assume that this will have, it will be having it. Okay, it will have two radiuses. Okay, one will be a smaller radius and the other one will be a larger radius. Fine. One will be a smaller radius. I'll call it as R1, and one will be a longer radius, larger radius, that will be called as R2. Fine. So if you have to find out a heat transfer between inside and to outside, okay, or from outside inside to outside or outside to inside, we use the formula 2 pi. Pi is 3.14. L is the length. This will be L. K is the conductivity. ठीक? T1. What is T1? T1 will be the inside temperature. This will be T1. Outside temperature will be T2. Understand? T1 shall be the inside temperature. T2 shall be the outside temperature. T1 will be the inside temperature. Fine. So it's a very basic, simple formula. If you get 2 Q is equal to 2 pi Lk T1 minus T2 divided by ln of R2 minus R1. Fine. Okay, this will be our third formula. You people should note it. Fine. Then another thing, fourth one, I will say is critical radius of insulation or critical thickness of insulation. Fine. Critical radius of insulation. See what happens. There is heat transfer. Okay, we have a body and there is a heat transfer going on. So what happens? Till a point, okay, we have a small pipe. Suppose we have a small pipe. Okay, it has a radius of R. Fine. So what we see for that R, if we add thickness, the heat transfer due to conduction will increase. If we add a thickness, the heat transfer due to conduction shall increase. If we add a thickness, the heat transfer shall increase because of the vibration of the electrons or vibration of the shells, electron shells. Because of the more frequency of collisions, we see that there is an enhancement in the heat transfer. But at a point, we move further and add an insulation, add a thickness, then we see that the heat transfer reduces. To a point, it reaches to a maximum peak point, and further when we add the thickness, when we add the thickness, we see that the conduction rate decreases. Understanding me? The point where...
Sir, repeat once again.
What happened?
Repeat once again.
Okay, fine. See, what happens? I'm talking about critical radius. Fine. I'm telling once if there is a pipe. Okay, I'm taking an example of a pipe or any material, any tube, any kind of thing that you have in your for your conduction. Okay, your setup is having a sphere. Your setup is having a cylinder. Suppose this is a cylinder. Let's leave pipe. There is a cylinder. Fine. There is a cylinder. Now cylinder has some thickness. Fine. Okay. So what I do, if I add the thickness, I see there is an increase in the conductivity. I keep on adding the thickness. Till a point I see there is my conductivity increases. And at one point I see that the conductivity starts to decrease now. If I add a thickness to a certain point, I see there is an enhancement in the conductivity of my material. But once I further add it, further go on adding to it, I see that the conductivity coefficient falls down. Fine. I see the conductivity coefficient going down. The point where I get the maximum conductivity, or the point from where further to which the conductivity starts to fall, the thickness of a material from where the conductivity of a material starts to fall is known as critical radius of insulation. That means from this point the conductivity shall go down. Understanding me? This concept is known as critical radius concept. Understanding me? So in your gate examination, what is being asked is about critical radius for a cylindrical system. Okay, they will ask you what is the critical radius for a cylinder. Okay, cylindrical system, or you can say cylinder. You will simply say it's K whole divided by heat transfer coefficient, convective heat coefficient. See, this will be RC. Okay. Then in some cases, they will be asking you, they won't be asking you critical thickness of for a cylinder. They will be asking you about, this will be A, this will be B. They will ask you critical radius of sphere. Okay, nothing changes, just simply multiply it by 2K by H naught. K is conductivity coefficient and H is convective coefficient, convective heat transfer coefficient. Okay, K by H, if they will be given, there will be given a lot of data for you. But if they are asking, they can give you anything. They will be giving length, they might be giving radii, they might be giving anything. But simply remember, if for a cylinder, if you are being asked about critical radius of thickness, or critical radius for a cylinder, simply say you have to do K by H. Simply do K by H and you get it. You are done. If they are asking you about sphere, simply write 2 into K by H and you are done. Fine. This was our fourth thing. Okay, this was a thing that was remaining. Okay. Okay. In my last lecture, I think I have, in my previous lecture, I don't know, was it a previous lecture or previous to that? Okay. Third or fourth lecture, I have given you some numbers. If you can see, they are called dimensionless numbers. Fine. So what happens when we are not able to exactly calculate the heat transfer? So what do? We take support of these dimensionless numbers. Fine. They give us an idea how to determine the heat transfer. Suppose there actually when what happens actually when we are using this Fourier heat transfer. If you can understand that we are we are only using a formula of minus K A dt by dx. Fine. So what is this x? This is thickness. We are assuming that there is no heat transfer. There are three axes. One is x axis, the other one will be y axis, the third one shall be the z axis. So why this formula is only applicable? Actually, this formula just gives us heat transfer when we assume there is no heat transfer from the y-axis and the z-axis. But in reality, there is three-dimensional heat transfer. Are you getting me? So what happens? Similarly, in this case, what happens in heat transfer? There is heat transfer in boundary layers, in from one phase to another phase. For a streamline phase, the heat transfer will be different. For a turbulent phase, the heat transfer won't be the same as that of the streamline phase. So to get an idea, to get a fair rich idea about how does the heat transfer happen, okay, how does it happen in forced convection? How does, if you have a heat source, it is dissipating same amount of energy, but you have two cases. One is a forced convection case and another is a free convection, no convection, free convection case. Okay, but the amount of heat transfer, the quantity of heat transfer will be different. So to normalize these things, we use the support of dimensionless numbers. Okay, now in your gate examinations, coming to the context of the gate, we'll only be sticking to the gate, because we are preparing for gate. We shall be maximizing our topics which are potentially being asked, or which have the potential to be asked. Okay, so I have jotted down some dimensionless numbers. If you can just recapitulate, I have provided you the notes, so if you can go through them, they are very basic dimensionless numbers. I have just elucidated them in the simplest possible manner. Okay, just remember, I feel I myself have seen that in match the following, they sometimes make up match the following cases. Okay, they will give a match the following. I think for 2 marks or 3 marks, even no, I think for 2 marks they will provide you match the following, and they will give you 4 numbers. Okay, suppose they will give you Biot number, Nusselt's number, Reynolds number, or some Grashof number. Then on the other end, they will provide you, like, is it done for convection? Is it done for convection? Is it done for magnetic heat transfer? Whatever it is. Or sometimes they will give you formulas. What is the formula Biot number? HL by K. You should be knowing it. What is Reynolds number? Rho V D by mu. You should be knowing these things. I have provided you the notes. Just go through them. They are, I think, 10 to 12 dimensionless numbers. You don't exactly need to know the numericals because they won't be asked in BTech level or in GATE examination. If you're going for masters, like we did in where, like in my masters, we had to use them a lot. We had to calculate we used to calculate everything from those dimensionless numbers. We used to first we were asked about like suppose we had to calculate the number of fins in an heat exchanger required. A plate heat exchanger is required. How many gaskets does the plate heat exchanger need, or how many tubes does how many plates we require in a plate heat exchanger. So to calculate those, to design those heat exchangers, we used to calculate these Nusselt numbers or other dimensionless numbers. But at BTech level, they only ask you about the number, its definition, and maybe at maximum what they will ask you is the formula. Okay, I have tried to jot down, I have tried to combine all those dimensionless numbers which have the potential to be asked, and I have provided you the notes and some of the very famous, I think I should say, pop or frequently asked dimensionless numbers I have provided in today's, repeated rather in today's lecture also. Like we have Prandtl number. Okay, first, where is it? The duster. Okay. Prandtl numbers. Okay. I'll just simply brief about few dimensionless numbers. It will give you an idea. Okay. Once you finish up with your masters, if from a good institute, then you just remember once this number comes up, so you have done so many numericals, you will be practicing so many numericals over it that Prandtl number mu CP by Q bus. Your mind will spontaneously give you a reply that it is mu CP by Q. So what is Prandtl number? It is basically, it helps in Prandtl number denoted by PR. Okay, it helps us. This Prandtl number helps us to calculate the heat transfer in case of free and forced convection. Fine. It has, sometimes they may ask you in GATE examination what is the ratio of how this Prandtl number is the ratio of. Then remember, it is the ratio of kinematic viscosity divided by the thermal viscosity. Prandtl number is a ratio of kinematic viscosity over thermal viscosity, thermal diffusivity, sorry. Okay, so Prandtl number, they may ask you, it is like rho Cp by K, mu Cp by K. Okay, mu is the dynamic viscosity, Cp is our specific heat, and K is the thermal conductivity. Fine, I have written it in on your notes. So sometimes they may ask you about Nusselt's number. Sometimes they may ask you about Nusselt's number. So remember, Nusselt's number will be HD by K. See, where H is your convective heat transfer coefficient. D is the equivalent dia. So what happens? You will remember. You will get it. You will get it in your mass or higher studies. So remember, sometimes what happens. This Nusselt's number, we mainly use it in shell and tube heat exchanger. Yeah, shell and tube heat exchanger. There is a kind of heat exchanger. Okay, there is one shell and there are a large number of tubes. Fine. So what we do, how to calculate the heat transfer? We calculate the heat transfer using Nusselt's number. Okay. For example, if the value of Nusselt's number is 10, below 10, so we have a different formula for that. If the value of Nusselt's number is larger than 10, then we have a different formula. We use a graph. You will, if you get into inshallah IIT or some good institute, you will learn about this thing, how to design a shell and tube exchanger. Okay. So why do we call? I wanted to actually, I've showed this formula because this diameter here. Remember, if Nusselt's number comes up in your GATE examination. So H will be convective heat transfer coefficient, K will be conductivity, but DC is the equivalent dia. So what we do, if you have a large number of tubes, fine, if you have a large number of tubes, and we need to calculate how much heat transfer, how much is the amount of heat transfer. So what we do, we don't use one dia, two dia, three dia, we just simply use an equivalent dia. Okay, we simply club those diameters and we just calculate the diameter of the all the tubes as a whole. We call it as an equivalent dia. Fine. Rest formula I have, I think, provided in your notes. Okay. Similarly, we have another number which is known as Peclet's number. Similarly, we have another number which is known as Peclet's number. So Peclet's number, we use this concept to calculate the transport phenomena, velocity or flow dimensions in a pipe. Okay. To calculate the flow dimension, if you want to calculate a heat transfer, okay, if you want to calculate heat transfer in a tube, fine, there is a flow of, there is something, some liquid is flowing through it, okay, in a liquid, and we want to calculate its if we wish to calculate the heat transfer, so we calculate it using Peclet's number. We see how much is the Peclet number. If Peclet number is large, then we say that the heat transfer is immense, it may be turbulent flow, and then we use a different formula for that. So to calculate the Peclet number, we see the formula is PC is equal to VD by alpha. Fine, where V is the velocity, D is the dia, and the alpha is always the thermal diffusivity. Fine. Similarly, another number which is more frequently being asked is about Grashoff's number. Fine. So what is Grashoff's number? See, so it is a ratio basically of a buoyant force and a viscous force. This is the ratio of GR. We call it as GR is called buoyant force divided by viscous force. In my GATE examination, I remember that there was a numerical asked about this question. Fine. So I had just remembered this formula. I just actually this was the largest formula. The formula was very long. So many of our students, many of my friends, or whomsoever I was always in contact with, they didn't remember. They said, "Yeah, itni lambi for it. This is a big formula. We won't come." But I thought like this is the perception of most of the students. They're leaving this formula. Why won't an examiner? Being an examiner, I will just ask this formula. Why? Because most of them are just saying that this is a large formula. It won't come. I remembered this formula, and luckily this formula had come. Okay, so I would say you should also remember this formula. Maybe you might get lucky too. Okay? It is G V delta T rho square. Just remember these formulas. L cube whole divided by mu square. Today I won't be remembering this formula, but that time I had this in my mind very much. Where beta is the G is gravity acceleration due to gravity. Okay? Beta is the coefficient of, it is a coefficient of volumetric expansion. Fine. Rho is the density. L is the length of the tube, and mu is the viscosity. Fine. Okay. I think I have just shown 4 dimensionless numbers. More, I think I have provided more. I think 10 to 12 more dimensionless numbers in your notes that I provided to you previously. Just go through them. Just remember them. Learn them. Just try to comprehend them very easy, very effectively. Just understand that if they ask you what is Grashoff's number, you should be able to identify which is the formula that is being that we need to know to find out the GR number. Okay, if they ask you about what is the ratio of GR number, then you should be spontaneously able to identify that it is buoyant force divided by viscous force. Fine. These are things that just you need to boost up. See what happens in GATE examinations. If you go on with a good rigorous study, you will always fetch you good marks, like 25 marks, 30 marks, they will fetch you. But if you want to go far ahead of just qualifying the examination, one is to qualify examination and the other one is to get a rank. See, you have to there are 3 levels in GATE. For preparing GATE, there are 3 levels. Just remember, 1, 2, 3. Fine. 1 is that you are beginning to prepare. Fine. This is where you are right now. ठीक, then you are thinking that uh, I should be able to cross this 25 marks. This is a qualifying. You are prepared, okay? You have qualified, and you are now having a rank. These are 3, 4 levels. If you are, I assume that we are all here right now. Fine. So prepare yourself that you don't reach only here. You have to reach here. Fine. If you just go on with a good comprehensive study, you may qualify. But qualifying, I don't think is sufficient. To get a rank, you need to do. For example, I showed you some formulas. These are the formulas that will only fetch you 1 mark. But remember, these one marks will add on and will transform your qualifying gate to getting a ranking gate. Fine. So what you try to do is like, okay, another thing I also wanted to share with you, like whenever I was preparing for gate, so I never targeted 25. I knew 25 to 30 will be the cutoff. Okay, but I didn't. My seniors, whomsoever I was in contact with, used to tell me, yeah, if you are targeting 25 to 30 marks, then take it for granted that you will never cross 20 marks. So what did they say? They said like target 70 marks. Prepare as if you are preparing to get 70 marks in gate. Even if you don't get 70, you will get 60. Even if you don't get 60, you will get 50. Even if you don't get 50, you will get 40. And trust me, this is true. If you are targeting for 70 marks, you won't get 70 marks, absolutely, but you will get somewhere 60, 50, 40. But if you are only targeting for 30 marks, I don't think how will you score 30 marks. You won't be able to cross 20. This is for granted. My seniors told me, and I believe now in it. I targeted 70 marks. समझ रहे हो? So somewhere I landed in a very good zone. Fine. So you have to target a good score of 70 marks. Fine. You will easily achieve 60. 60 is nowhere. 60 is so simple to get. It was my good day. I solved, there were 60 questions and I kept on solving. I just solved whatever I knew I could. So I think I solved some 42 or 45 questions. And luckily, one good thing happened. No, luckily, no. I forgot to solve two. I didn't get a script sheet. They will give you a script pad that day. In 2015, I think they used to give a script pad, a hard note book. After that, they won't give you. I just finished up for me, and I was left with last 10 minutes, and I couldn't solve those two questions. Then I have for the next 2 months, I was only regretting. Will those 2 marks will those 2 marks sink me, or they will just make me feel regrettable for the whole life? I was thinking like in my when I was finally expecting the result day in the March. I was thinking like, oh, should I be getting 25? Sometimes I felt like I will be getting 25. Sometimes I felt like I will be getting 15. Sometimes I felt like I will be getting 60. Sometimes 50. So luckily I got in a good zone above 50. So what I was telling you, just don't leave anything. They will be asking from very specific, choosy questions. Gate examiners, actually, what happened? They are mostly from IITs. IIT professor, IIT Kharagpur sets the paper for food every year. I know it. Okay, and whatever they are asking from last 10 years, 15 years, they'll continue to ask in the next examination. What you have to do is just be choosy. They are very choosy. You have to be smart. You have to also be very choosy. You know this dimensionless number. It is being asked. Just prepare for it very well. Just don't leave it. Just leave another topic. We have to leave 10 topics, but we have to clear the 11th topic in such a manner that whatever is being asked in the 11th topic, you will be able to answer that thing. You don't have to read 11 things. You have to read only one thing or two. Out of 10 things, you only need to study one thing. But that one thing you need to study in depth. Gate is all about depth. Net examination is a surface exam, shallow examination. They will ask everything, but they will not ask anything in depth. So there is a difference between net examination, ICR net examination, and gate examination. Gate is all about depth. They check your concept. They check your quantum of knowledge. But sorry, quantum of concept. But in net examination, it is mostly a mugging up exam. They'll only ask about numbers, quantity, values, dimensions. So net will be like, if you are able to qualify gate, the net is a cakewalk for you, all of you. Okay, so without wasting time, I shall move on to our next concept is heat transfer for transient conditions. Okay, lumped capacitance. Fine. So what is lumped capacitance? In food materials mostly, we see that, okay, for unsteady state, okay, I told you in our last class, I told there are different modes of heat transfer, different conditions of heat transfer. One is a steady state condition, the other one is the unsteady state heat condition. So unsteady means that the heat transfer depends upon location as well as time. But what happens, what you see in various food products, okay, we see that heat transfer is uniform at all the places. This point, 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 it's all uniform. But it varies only with time. Okay, it's an unsteady state heat transfer, and the heat transfer is uniform inside the body. There is a uniform heat transfer, but it varies with time. Okay, it only is varying with time. So for those heat transfer conditions where there is the where the heat transfer is only dependent upon time. ठीक है? Interior temperature of some bodies remain essentially uniform. ठीक है? But what happens? The interior temperature remains uniform with respect to space, but with respect to time it changes. We call such a situation is known as lumped system heat transfer, lumped capacitance heat transfer. Okay, or lumped system heat transfer we call it. See, so what happens in this kind of heat transfer? Okay, I won't go with the derivation because we don't need it. Okay, so what happens? Just what happened? I think I lost the alignment. Very bad. Okay, great. Maybe in a few weeks' time we will be we won't be requiring a board. Okay. I may be getting a pen tab. So, what I was telling, there are certain conditions in our food system where we have unsteady state heat transfer. Fine. So, what happens there? There is, with respect to time, the heat transfer changes. Okay, it's an unsteady state heat transfer, but essentially inside the body, the temperature is same. So, suppose we say that Ti is the initial temperature. The temperature only changes with respect to time. Fine. So we call that let the inside temperature be Ti. Okay. I'll remove the circles else you will get confused. This is inside temperature called Ti. And the outside temperature shall be T infinity. Fine. Such that Ti is greater than T infinity. Fine. So what happens here? We have a condition. Okay, and the condition says that we have a certain product and its temperature with respect to time keeps changing, but inside at all points the temperature is same. Okay, the temperature changes, but it is uniformly changing. Whatever will be the temperature, it will be the temperature for the whole body. It won't be for any specific point. Outer point there will be 10 degree and inside point there will be 2 degrees, or outer point there will be 100 degree and inside point there will be 85. It will be uniform. If it is an unsteady state condition, the outer temperature is 100, inside temperature will be 100. Outer temperature is 50, inside temperature will be 50. But the temperature may change with respect to time. So in that case, we say that the inside temperature of our product is Ti. Fine. And the outside temperature is T infinity. So such that the condition is such that the Ti is greater than T infinity. The inside temperature shall be greater than in T infinity. In that case, the formula to calculate the time or the temperature is T minus T infinity divided by T initial minus T infinity fine, is equal to e raised power minus b t. Fine, where b is ha whole divided by, where b is h into a rho divided by rho v c p. Fine. So to calculate the temperature of body at any point, at any time, we have a formula, and the formula says T minus T infinity. Wait a second. Oh. Okay. So we have a formula which says to calculate the temperature or time or any kind of any other feature such as convective heat transfer coefficient, or you have to calculate area, okay, or density, volume, heat capacity, specific heat, sorry. So in an unsteady state condition where the temperature of the body with respect to time only keeps on changing, but with respect to space it is same uniformly. The temperature distribution inside the body is same at all the points, but it changes with respect to time. If you want to calculate the temperature of a body after time t, so we have a formula for that. T, I will call it as tt. Why tt? T temperature at time t. Okay, suppose we have a body, suppose we have a meat ball, or suppose we pour in potato. Fine, we pour a raw potato, peeled potato inside some soup. Okay, so and we assume that it's a lump system. Lump system means potato acts as a lump. The temperature inside the potato is uniform. If it is out on the surface 50 degree, inside surface it will be also, inside point it will be also 50 degrees only. So if we want to calculate the temperature of the potato after 50 minutes or after 20 minutes, what will we do? We will simply see temperature of potato after 50 minutes is equal to what is the temperature of external temperature or the infinite environment temperature in which it is put in, minus initial temperature of the potato, minus the infinity temperature or the surface temperature, sorry, environment temperature in which the potato is being, or the soup in which the potato is being put in, and we will just simply equalize it with exponent e, which is exponent minus raised power minus bt, where b is a constant and it has a value of HA divided by rho VCP. Where H is the convective heat transfer coefficient, A will be the area of the potato, rho will be the density, V will be the volume of the potato, CP will be the specific heat. Fine. This is called as the lumped circuit. This question may be even asked to you for around, I guess around it is usually asked, if it is asked for a 2 marks question. Okay, in I think 2018 or 17 this question had come in your gate examinations. XE. Maybe Excel also, I don't exactly remember. So we have on this meatball or in this lumped capacitance question, we have a question. Sorry, if lumped capacitance case, we have a question. If you all have note, which I provided just now, a meatball with a radius of 25.4 mm. Okay, let's make it a activity question. Fine. I won't solve this question, but however, I'll tell what to do. I want you people to solve it. Fine. If you don't have a calculator, get it. Get it in. We'll wait for a minute or so. Everybody should get a calculator right now. Fine. Or I think I expect that you people may be having it with you this moment. So what is being asked? It is a meatball with a radius of 25.4 mm at a temperature of 790 Kelvin. Okay, this is a meatball. There is a meatball, and which is at a temperature of 790 Kelvin. Is suddenly plunged into a medium. It is supposed plunged in water. Okay, and the water is having a temperature of 395 Kelvin. That means our body is meatball, and we are putting it in an infinity temperature or the surrounding temperature, which is 395 Kelvin. Assume convection heat transfer coefficient of 11.5 watt per meter square Kelvin, and take an average physical properties of conductivity equal to 44 watt per meter Kelvin, density 7850 kg per meter cube, and specific heat of 0.4606. The temperature of the meatball after 1 hour is. Now it is saying that okay, the meatball is at a certain temperature, and we are putting the meatball in a the meatball is at a certain temperature, and we are putting the meatball in a medium. Fine. So such that the temperature of the initial temperature of the meatball is 795 Kelvin, and the temp, which is the Ti, and the infinity temperature. The temperature of the medium is 395. Ti means T infinity is 395 Kelvin. We have to find, what do we have to find? We have to find the temperature after 1 hour or 60 minutes or 1 hour. We will say temperature at 1 hour. Minus, what is the formula to calculate such the temperature after 1 hour? We will say T minus T infinity divided by Ti minus T infinity is equal to e raised power minus Bt. Fine. Okay. Can anybody solve this question?
Yes, sir.
Okay, great. You people tell me what are the steps or what are the values that I need to put in. For T1R, what do I need to put in?
So nothing, that's to be found out.
Great. So T after 1 hour. Okay, minus, what is T infinity?
395 Kelvin.
Divided by
790 minus
790 or 795? 790, okay.
790 minus 395.
Great. Is equal to. Okay. What else is given?
values for calculating B.
Okay. First, what we will do, we will calculate B. Fine. I think I should have done it earlier. Where is the duster? Okay. Let's calculate B. What was the value of B? H into A divided by
Rho
rho
CP.
V Cp. Fine. What do I need to put in for H?
11.5.
Great. 11.5. Then A. Since it is meatball, it's a ball. So what we assume that the shape has to be
Sphere.
spherical. Okay. What's the area for a sphere?
2 pi r.
2 pi r or 4 pi r? 2 pi r is a area.
It's 4 pi r.
4 pi r or 4 pi r square?
4 pi r.
Square.
4 pi r square.
Fine. Then rho, how much is the rho given? 7850 into V. How much is the V?
4 by volume
That's
of
to be
sphere.
calculated. 4 by 3 pi
What
r
is the
cube.
formula for volume of a sphere?
4 by
4 by
3
3
pi
pi
r
r
cube.
cube.
4 by 3 pi r cube. Fine, great. And then what is the term remaining?
Specific
See,
heat.
what is the specific heat? 460. 0.46.
0.46.
Great. Fine. So if I say do one thing, r cube, the cube will cancel and r square will go. Pi will go, 4 will go, 4 will go. So I think it's 3 by r. Fine. Am I right? Or I'm doing it wrong?
No, it's correct.
Yes, sir, 3 by r.
Okay. 11.5 into 3 divided by 7850 into r. Now, so remember, you had you had density, it is kg per meter cube. So the thing is that you have to be very vigilant at this point, that the term that is being given is in meters. So r, how much it was given? 25.4 mm. How much is 25.4 mm? How many meters?
Divided by 1000.
Great. Tell me the value. 0.025.
0.02.
0.025.
4. Great. Then multiplied by 0.4606. So can anybody tell me how much is the amount? Can you solve it? Okay, now from this point I leave it here. Okay, from this point, everybody take a pen, take a calculator, and give me a value. Give me the value. Now,
Sir,
this
one
will be our B. Okay, we have formula T after 1 hour into minus how much? 395 whole divided by how much it was? T initial, that was 790 minus 395 is equal to e raised power minus b into. Now T. Okay, T, how much is the T? After how much time I need to know the temperature?
1 hour.
So what will I write?
1 hour.
In seconds.
1 hour is 3600. Okay.
Seconds.
Anybody? Everybody should calculate it from here. I'll leave it on. I'll give 3 minutes. Okay, 3 to 4 minutes. Let's solve it. Okay.
Sir, sorry to interrupt, but there is one doubt.
Please.
Sir, in notes, like where you have written the formula,
6
they before this numerical question,
Okay.
page number 6.
Page number 6, yeah.
So there B equal to HA divided by
Okay, just forget
LP.
this. There is a confusion. Just forget about this derivation. What I have given you in the at the end, I have rubbed it S. Actually, I didn't. C was S.
No problem, sir.
Just focus on the formula. Okay.
Okay, sir. Thank you, sir.
Okay. Anybody able to solve this question? What should I write from here on? Anybody who can dictate me what should I write?
Yes, sir.
Okay. Great. Tell me what I should write here. Okay, what is B? How much is the B? Should I get the calculator or you people will do it?
So 0.3756.
0.37.
So 0.3575.
0.37.
37.
35.
0.3766.
0.37.
Okay, 0.37. Fine. Now we have T 1 hour minus 395 whole divided by 790 minus 395 is equal to e raised power minus how much? 0.37 into 3600. What should I write finally further? How much is e? Just right hand side. Give me the value of right hand side. I think I have written it 78.8. You're getting it the same? Okay, how much is 790 minus 395?
395.
395.
That means 395 into how? Anybody who's able to solve this from calculator? 1 hour minus 395 is equal to 395 into what is this term? Okay, I think from here it's all calculator work. I can't simplify it further. Just see what is this term, write it here, and take this 1R is equal to 3, this term plus 395. Okay, this will be your answer. I have written some 473, I calculated it. Kelvin, it should be the answer. Okay. So this was lumped capacitance. If sometimes this question comes up, just simply solve it with this approach. Fine.
Hello, sir.
Uh-huh.
So if we type e to the power minus 0.37 into 3600, the result is 0. My
How is it?
calculator showing the result is 0.
Yes, sir. Same here.
Yes, sir. Same.
Yes, sir.
And the
Same
total
here.
answer is 790.
Okay, fine. So this is a issue. I don't have a calculator right now here. Tomorrow morning or tomorrow evening, I'll just take a 5-minute video or a 5-minute class. We will just do it. Okay, I'll show how to do it. Fine. I left it in my office only.
Okay, sir.
Mhm. Okay, so I'll just touch few more points. Okay, these are the questions that I found in your gate last 10 question papers of your gate examinations. Fine, they are very simple. Okay, before moving on, before starting the unit operations, we will just brush them up. I would rather say we are brushing them up. So simple, what is density? Sometimes they will ask you about density. Fine, so we know density is rho, which is equal to mass over volume. Fine, okay, that is kg per meter cube. Fine. Now, what they will sometimes ask you about bulk density. Fine. So, what is bulk density? Bulk density is when you leave least possible airspace, okay, inside a volume, or you fill, there's a container, suppose there's a borosil container, and you want to know the volume, okay, you put it in, fine, it's there, it's simple density or true density. But what you do now, you try to compress it. There are two conditions how you can determine density. Okay? So suppose there is a powder, you sometimes see, then you filled it, there is some space remaining in the powder, there are a lot of voids that are remaining inside the box or some space. So once you fill it and you see how much is the quantity, you will say that this is a true density. Okay, this is a density. But sometimes what you do, you just compress it from the top. You compress it to such a level there is least possible void ratio in it. There is a least possible space for any kind of void or porosity to be there. Once you compress it, stock it down, okay, the density at that point will be called as bulk density. Okay, when you are packing it to a maximum level, when you are packing it as a maximum compression, fine, such that the whole space is being covered, there is no space, which is, we usually say there is no space for any void. Okay, there is no space for any porosity. At that point, we call it as bulk density. Okay, this is density at bulk. After that, there is no possibility of any further increase in the density. This is the maximum density that is possible, which is known as bulk density. The maximum density that is possible of any material is called as bulk density. Fine. And if you just want to know the density at any point of time, okay, that is freely, readily available, that we call it as true density. If you are calculating the density at a maximum compression level, the highest density that is possible for any particular material is called as bulk density. Fine. Then we have a concept of true density. Fine. We denote it by rho t. Fine. So it is density at any point. It will comprise of all the voids, porosity. It will comprise of the porosity as well as the material. The density at any point, the real-time density at any point will be known as true density. Fine. And if you want to find out the density of a large number of materials, then we say simply say, what do? We combine them. We combine a large group of if you have a density of a composite material which is having a different kind of different substances, different material, different molecules added in it. We simply what we do, we do summation of xi, which is the volumetric fraction multiplied by its density. Fine, rho I. Or what will we do? We will say rho T 1 by summation of 1 by rho I by xi. Yeah, sorry, xi by x m by rho I, where xm is the mass fraction. Okay, we summate it. In your master's level, probably you will deal a lot of numericals to for finding out true density of material. In this for gate examination, I don't think this will be asked, but what they ask mainly is the relationship between bulk density and true density. Okay, so true density in terms of volume fraction, it is summation of mass fraction of volume multiplied by density, and in terms of mass fraction, it is 1 over summation of mass fraction into rho I. Mass fraction will be 1, and the summation of all the mass fraction or the volume fraction shall be 1, and it will be obviously for a single component it will be less than 1. If you are finding it for the true density for a single component, it will be in some between 0 to 1. Okay, you don't need to know this thing. Okay, true density they will not ask you this level. Okay, then what is important to know is porosity. What is porosity? It is that fraction which is occupied by air. Okay, we see that if we fill a container with some material, there is some kind of air that is present in there. Suppose there are grapes. Okay, we have 20 grapes and we are putting it in a borosil 500 beaker. Do you think the beaker shall be contained with all the grapes? No, there will be some gaps left for air. Understanding me? Because of the dimension of the product, there will be some gaps that will be filled up by air. So to calculate those gaps or the air, we call it as we use the concept of porosity. What is porosity? Simply air volume whole divided by the total volume. We calculate porosity. Porosity is the air volume divided by the total volume. Fine. Okay. Now, what is being frequently asked is not, they won't ask you about porosity. What they will frequently ask you about is the numericals which will be pertaining to the relationship between true density, bulk density, and porosity. Okay. So always remember, porosity is equal to 1 minus rho B divided by rho T. Fine. Porosity is equal to 1 minus bulk density divided by its true density. Always remember this thing. Fine. This will be I think this is a frequently asked question. FAQ we call it. This is FAQ. We call it as FAQ. Okay, this is a frequently asked question. How do we calculate porosity? We have for the porosity, to calculate the porosity, we have a formula. Porosity is equal to 1 minus rho B by rho T. Fine. 1 minus density, bulk density divided by the true density. Fine. Then we will be solving numericals. I think, or I will be giving you a worksheet. Okay, this is a very simple thing. Okay, you can do it. I will be giving you this Saturday. I'm not here. Sunday I shall try. Okay, Sunday I shall try to give you. Okay, Sunday I shall try for a class because last week I missed the class. Now I am not able to take it. I wasn't able to take it in the past few days because of some work that I had. Or okay, so I think this Sunday I shall be trying to take your class probably. So okay, then we have another thing is a concept called sphericity. See, once you are having a product in your hand, okay, generally a rounded product, then you try to figure it out. What is this shape of the product. How is the shape of a product? Okay, in your engineering terms, in your engineering calculations, what you do, you try to figure out how is the product now. Okay, so how do we do that? We say, suppose there is a sphere. Okay, we call it as a perfect sphere. Suppose, okay, we have a spherical body, and we say that its sphericity, okay, is 1. Okay, we have a perfect sphere. Perfect sphere, how do we determine? The volume will be 4 pi r cube. The area will be same. The circle, the dimensions or the curve radius of curvature will be exactly as of a perfect spherical body. We call it as a perfect sphere. Okay, so and we take the sphericity. We are talking about the concept of sphericity. Okay, we say that is, if there is a, suppose there is a perfectly spherical body, okay, and we say that its sphericity, okay, its dimensions, its property, its everything is of a perfect sphere, and we call it as, we say that the sphericity is 1. The sphericity of a sphere is 1. Okay, sphere means it's a perfectly spherical body. It will have volumes of a perfect sphere. It will have area, radius of curvatures. Everything will be it, whatever it will possess, it will be possessing of a perfectly spherical body. We call it as a sphere. We use it most often in mathematics. Fine, but when we just now try to relate it with our food industry, food products, mainly what you will be encountering it with will be our fruit products. Okay, we have an apple, for example. Now, apple will be a it will be a spherical. I won't say spherical. It will be a 3-dimensional rounded body. I will call it, definitely I will call it. But it won't be of a perfect sphere. Okay, there will be some deviations. Okay, like there is an apple. Okay, this is apple. So at some points I will feel like, okay, yeah, it is showing the spherical. It is showing complete sphericity. But at some point I say, no, this is not a sphere, this is a linear body. So there are some deviation. At some point there is a deviation. At some point that is matching matching the curves of a sphere, properties of a sphere. At some point it is not matching. So what do I say? I say if there is sphericity of a body, perfectly spherical body is 1, I will try to relate it with how close is my product as compared to a perfect sphere. Fine. How much it is deviating? On the basis of those deviations, I will say the sphericity of a product is something. Suppose this is an apple. A perfectly spherical body inside an apple, in its circumscribing space, I will take it as 1. Fine. And what I say, in comparison to that body, the sphericity is just, it's not match. The deviation is something else. Fine. I will say, suppose okay, I'll say this, there is a body. Okay, there is a spherical body. Its sphericity is 1, but with respect to that, it will come only 0.5. For my apple, the sphericity will be 0.5. What does that 0.5 mean? That 0.5 means with respect to a perfect sphere, if I take the sphericity as 1, my product, which is apple, it is only matching half the properties of that sphere. Fine. The deviations will be almost 50%. My product is having 50% deviations from a perfect sphere. It is not a sphere. Suppose some product is having a sphericity of 0.9. Okay, I'll say, okay, man, it is matching maximum properties from a sphere. It is almost a completely spherical body. Sometimes my product will only have a sphericity of 0.1. I'll say, okay, yeah, it's not having any kind of spherical properties. It won't be even sphere, because it is way too far beyond being relatively closer to a sphere. 0.1 means only 10% matching for a sphere. 0.9 means 90% it is matching to the properties of a sphere. 0.5 it means 50% properties matching to of a perfectly spherical body. Fine. So this is a concept that you will be mainly using for your to calculate the engineering properties of your food materials. You must have studied it in your I think BTech also in some courses, if the teacher has taught. So how do we calculate it? It's simple. Volume of solid particle or solid product, whole divided by volume of the circumscribed sphere. Volume of circumscribed sphere. Fine. Okay. I'll just write the formula. Okay. If there is a food product, it has 3 dimensions. Fine. We call it as length, breadth, and height. Okay. It's A into B into C. Fine. Cube root. And the smallest dimension of that product, okay, we will divide it with the smallest, because we are talking about the smallest volume of the circumscribed sphere. The smallest dimension we shall take it and divide it by. It's simple. Sphericity will be equal to cube root of length, breadth, and length, breadth, height divided by length or breadth or height, whatever is the smallest. Because we are talking about if there is a product, suppose this is our food product. So smallest sphere that is possible will be our the radius of the smallest sphere possible will be our length. Fine. So sphericity we will do the numericals on sphericity too, or I will provide you a worksheet. Okay, equivalent dia is simply what we will do. We just cube root the dimensions, cube root the volume, cube root the volume. Okay, we will get the equivalent dia. Fine. Suppose there is a sphere. Okay. Fine. It will have, this will be R, this will be R, this will be R. But if it is a food product, okay, if we call it as diameter, this will be this will be X, this will be Y, this will be Z. So if we have 3 dimensions, so to calculate the equivalent dia, we will simply, what will we do? We will just cube root R length into breadth into height, or AB into C, whatever it is mentioned. Fine. This is okay. Overrun. Another thing that is I found in your GATE examination paper, for this I will show numericals. Okay, I'll just collect it with Sunday. Probably we will do numericals on overrun. Overrun is important. I think it can't be left. Okay. Okay, I'll just do one thing. Next class, I will just compile 10, 20, 10, 15 numericals, and we will just try to solve it in this video lecture only. In that video lecture, I mean to say. Okay. So, what is overrun? Sometimes we see that there is a product volume, but the product is inflated. Okay, the product is, mainly in case of whipped ice cream, whipped creams or ice creams, we see that the product has been the space within the product has been grasped by air, has been filled up, occupied up by air. Okay, so to calculate the overrun, to calculate how much have we exceeded the space, how much the air has exceeded the space within the product, we use the concept of overrun. What is overrun? Overrun is increase in volume. Simply, this is a very simple numerical. Increase in volume whole divided by the original volume. Fine. If we have to calculate the overrun, we simply, what do? We simply calculate the increase in the volume and just divided it by the original volume. Fine. We will do numericals over it. I will show numericals in next class. This is a very important topic. Okay, we can't leave it. Okay, I'll just leave it here, and I'll just try to get 3-4 numericals, or maybe more, over this concept, because I have found that overrun is a frequently asked question. Okay. Then there are a few numericals, I think. Yeah. Okay. Fine. Okay, the first one is the one thing I forgot to tell, sphericity. Okay, sphericity we always, okay, yeah. We don't take the smallest radius here, we only take the length. Fine. Length into sphericity, we take the length, cube root of length into breadth into height divided by length. Fine. I remembered it now. We take it in roundness ratio, I think. Okay, here in sphericity we take the length only. Fine. We have a question. If you are seeing the notes that I have provided, if the length, breadth, and thickness of a rice grain are 7 mm, 3 mm, and 2 mm respectively, what is the sphericity of the grain? Fine. I was confused with roundness ratio, roundness and sphericity. Okay, we are only dealing here with sphericity. So remember, for sphericity, we have length, breadth, height divided by length. So if there is a given condition, length is given how much? 7 mm. Breadth is 3 mm. And height is how much? 2 mm. This is a rice grain. Fine. We are telling length is 7 mm. Fine. The breadth is a three-dimensional figure. X axis, Y axis, and Z axis. Okay, X is itna, Y's breadth is 3 mm, and Z thickness is 2 mm. We are being asked to calculate the sphericity. Simply, what will we do? We'll cube root the length into breadth into height and divide it by length. Fine. We have 7 into 3 into 2, 7 into 3 into 2. We will cube root 7 into 3 into 2 and divide it by 7. We will get 0.49 or 0.5. What does this 0.5 mean? That means if there is a cube having same dimensions, okay, having same volume, if there is a cube which is having same volumes as that of this rice, so the relative curvature, relative deviation, the deviations of this rice is almost 50%. It is only showing 50% the property of a sphere. It's not a sphere. We can't call it as a sphere. Sphere, if it would be, we can just determine the shape of this body. If it is only 50% relating to a perfect sphere, we say no, this can't be a perfectly spherical body. If it is about 0.75 the sphericity, then we say yeah, this is a sphere. This is relatively having the properties correlating with that of a sphere. Understanding me? Okay. Then we have another numerical. I think this you can do. Wait a second. Processing. Fine. Okay. We have if the bulk density of a particulate matter is 600 and true density is itna, find the porosity. We are being asked to find the porosity. So I told you the formula for porosity is 1 minus bulk density divided by true density. So 1 minus bulk density is how much? 600.
600.
By 1000. 1, 2, 1, 2. How much it is?
0.4.
Okay.
0.4.
0.40%. Okay, the porosity, that means 40% of the volume is having only air. Fine. Similarly, there is another numerical that I have shown. Okay. I have written the true density. The true density and the bulk density of rice grains are 1230 kg per meter cube and 740 kg per meter cube respectively. And that of wheat grains are 1360 kg per meter cube and 650 kg per meter cube. Fine. What happened? Okay. The volume fractions of a bed of rice and that of wheat is simply volume fraction, void fraction, or porosity. They will be one and the same thing. Fine. So what you need to calculate is simply void ratio or porosity. Again, 1 minus rho B by rho T. What will be in case of wheat? First, let's calculate about wheat. What is 1 minus what is rho B? For wheat, what is rho? What is bulk density of wheat?
1360.
650.
650 is, I think, 650 is the bulk density. 650 is the bulk density and true density is 1350. So if you want to calculate the porosity of wheat, we will calculate how much it is. 0.522. Fine. Similarly, if we wish to calculate the porosity of
0.4.
rice, 1 minus, it will be 740 by 1230. 740 whole divided by 1230. This will be how much it is? 0.4.
0.4.
Great. So this is how to calculate porosity. In next class, we will be, I think I have some more formulas, okay, which are frequently asked. I shall be covering up those, and I have to show some more numericals before we move on to our drawing operations, so that I'm able to complete everything. I'm able to cover up every possible question that will be asked, potentially be asked, from heat transfer, mass transfer, introduction to heat transfer, sorry, introduction to food engineering, or that elementary engineering properties chapter, before we can move on to our unit operations. Then we have unit operations of drying, okay, then we have thermal processing, freezing, refrigeration. We will subsequently be moving on to those then. Okay, so I will leave it up here only for today, and I will try to get it arrange for a class on Sunday. If not possible, then next week. I will try, but my level best to get the class on Sunday. Fine, everybody?
Yes, sir.
Yes, sir.
Okay.
Okay, sir.
Thank you, sir.